Hi, grade 12s. In this video, I'm going to explain the material in lesson 55. So the game plan for the period basically is quite similar to what you've been doing for the past couple of days. Um, there's a lesson today, and I posted the answers to lesson 55 along with the textbook questions in Google Classroom. So after you watch this video, you can then spend the rest of the period filling in the handout and doing the textbook questions. And then if you finish the textbook questions, then you can work on your quantum physics assignment or your culminating. Now, I'll just say from the beginning, before we get into the material in this lesson, that I don't plan to go through this example step by step in this video. Okay, just for the sake of time, I don't want the video to be super long. So, like I've been doing for the past couple of days, I'll just post the answers in Google Classroom, and you can just refer to those answers and just fill in the answer that way. Okay, of course, I would encourage you to try doing these examples on your own before looking at the answers in Google Classroom. So just give this question a try before you actually look at what I've posted. All right, so I'll scroll back to the beginning. And yeah, we're on lesson 55 now. So lesson 55 is on the Bohr model. Now, some of you may be a little bit surprised by today's topic because this might sound more like chemistry instead of physics. But you'll see that in today's lesson, basically, we're going to start applying quantum mechanics to our understanding of the atom. In order to really understand what an atom is and how an atom works, you need to invoke quantum mechanics. And so, chemistry and physics really are quite closely related to each other. You could almost say that chemistry is built on a foundation of quantum mechanics because you can't really explain like the periodic table without some understanding of quantum mechanics, as it turns out. Now, I did make a comment in Google Classroom that this material might look kind of intimidating, right? So if we just go to our third page here and the fourth page, you can see some of the math starts looking kind of crazy. You'll see, though, that it's not actually too bad, I don't think. It's worse than it looks. It's not as bad as it looks. The reason why it looks so terrible is simply because there's just like a lot of constants involved. So there's a lot of symbols, which makes it look kind of scary, but it's not too bad. Like in this equation, for example, H, we know already, is Planck's constant. We all know what pi is. ME is the mass of an electron. Okay, so these are all constants that we're familiar with. It's just a lot of constants all at once in the equation, so that makes it look kind of crazy, but I don't think it's too bad. All right. So yeah, let's start just by looking at physicists' understanding of the atom before quantum mechanics came around. All right, so in the late 1800s and early 1900s, scientists had shown that an atom has a very dense, positively charged mass in its center, which we now call the nucleus of the atom. And electrons, which are negatively charged, reside in the space around the nucleus. Okay, and in particular, it was a physicist named Ernest Rutherford and some colleagues at the University of Manchester that did a very famous experiment in 1911 called the gold foil experiment. It basically involved firing a particular type of radioactive particle at a very thin sheet of gold foil and looking at how those particles got deflected when they passed through the foil. And their results showed that these particles had to be colliding with something that was very dense and positively charged. And so they were kind of able to deduce the structure of the atom in this way. They were able to find out that there's very dense, positively charged nucleus in the center, and that the negatively charged particles reside in the space around it. Now, whenever this discovery was made, people wondered exactly what an atom looked like. And, if you've done an experiment in which you've found that there's a dense positively charged mass in the center with negatively charged electrons moving around it, you might think that an atom would look something like this. This is just kind of a common sense way of picturing the atom. In this model of the atom, it looks a bit like a solar system. It's almost like we have planets orbiting around a sun. It's kind of a similar idea. So the thinking was that our atom had electrons orbiting around the nucleus. And in the case of a solar system, of course, it's the force of gravity that keeps planets in orbit. And so in the case of our atom, it's the Coulomb force between the opposite charges that are keeping the electrons in orbit. So that was the thinking in the year 1911, whenever Ernest Rutherford and his colleagues did the experiment. They put forth this model, and they suggested that this is what an atom looks like. This is now sometimes called the Rutherford planetary model, simply because it's a model that treats an atom as if the electrons are like planets orbiting around a star. Now, this picture of the atom is very simple and straightforward, and I'm sure that you've probably seen a picture like this in your previous science classes or in chemistry class. But the reality is that this simplified view of the atom actually has some major problems. Some major problems, in fact, just based on ideas that we've been learning about in this course already. So what sort of problems are there with this model? Well, for one thing, I'll just scroll down here. When we learned about electromagnetic waves, we learned that electromagnetic waves are created anytime a charge accelerates. So if an electron, for example, accelerates, we learned that electromagnetic waves are emitted as a result of that. And this is a problem because in our model of the atom here, that's treating the electrons as planets orbiting around a star, these electrons are clearly accelerating. And so according to physicists' understanding of electromagnetic waves at the time, that suggested that if the electron was accelerating like this, it would have to be emitting electromagnetic waves, and that it would actually lose energy from emitting those waves. So it would lose energy, and the energy would be carried away in the electromagnetic wave. And so, if this model was actually taken seriously, and we actually viewed the atom to simply be a positively charged nucleus with electrons orbiting around it, this is what would happen. You would basically have an electron that loses energy in the form of electromagnetic waves. And as it loses energy, the radius of its orbit would decrease, and it would basically spiral towards the nucleus, and the atom basically would collapse. So in this image, we can see our electron losing energy in the form of electromagnetic waves and just spiraling in towards the center of the atom, causing the atom to collapse. And physicists actually did some detailed calculations to determine how long it would take for this to happen. And as it says in the handout, they found that the collapse of an atom would only occur within 10 to the minus 8 seconds. So that's certainly a problem with this model. If it's suggesting that, atoms are just not stable at all and that they would collapse within 10 to the minus 8 seconds. This is, of course, not what we observe. We observe atoms as being very stable. So this is definitely a major problem with Rutherford's planetary model. Now, another problem with Rutherford's planetary model is that it fails to explain the emission spectra of elements. And if we had more time in this course, I would have done an entire lesson on emission spectra, but we've kind of lost some days, so I'll just kind of give you a brief rundown on how emission spectra work. So a continuous spectrum, such as that from white light, usually originates from a heated solid. So this image shows a continuous spectrum. Continuous just basically means that you can see a range of colors in the spectrum. So you can see the colors from red to violet. This is a continuous spectrum. Now, this type of spectrum you would usually get from a heated solid because this type of spectrum results from atoms interacting with their neighbors. So in a solid, the atoms are closely packed together. And then whenever they interact with each other, they basically emit a range of different energies. And if they're emitting a range of energies, we see that as a range of different wavelengths. So we have a range of colors in the spectrum. Okay, this of course is the type of spectrum that we get from the sun. And so the sun is a heated mass of hydrogen and helium. All of these atoms are interacting with each other. And so this is why we get this continuous spectrum from the sun. Now, physicists had observed that whenever you take a hot, rarefied gas, that you end up with an entirely different type of emission spectra. So what does rarefied mean, first of all? It just means that the gas is under a low pressure. So if you take a gas and put it under low pressure, you have a situation where the atoms are far enough apart so that they're not really interacting with their neighbors anymore. And that means that any light emitted is going to come from individual isolated atoms. And if you heat up this gas, you're going to see some light from the heated gas. And what is that light coming from exactly? Well, it basically comes from the atoms losing energy after they've cooled. So if you heat up a gas, you're exciting the atoms, giving them some energy. When the atoms release that energy, we see it as light. It gets released in the form of light. And so if you heat a gas under low pressure and just look at the emission spectrum, again, since you don't have this complication with the atoms interacting with their neighbors, it actually provides a good way to better understand the structure of atoms themselves. And these are the types of spectra that you get whenever you heat up a gas under low pressure and look at the light that comes off of it. This is the spectrum from hydrogen, for example. This is mercury. This is neon. And at the beginning of the 19th century, people were observing, and they knew that you get these types of spectrum that we call a discrete emission spectrum. So a discrete emission spectrum, as you can probably guess, is just one where you're only getting specific colors of light. So a continuous spectrum is where you're getting a range, like we see up here. A discrete emission spectrum is where you're only getting specific colors. And you're not really getting any colors in between the specific ones that you get. And how is this emission spectrum created? If you pass the light through a spectroscope is just a device that spreads out the light according to its different wavelengths. And so, yeah, we're seeing the light from some hot rarefied hydrogen gas being spread out so that we can see the different wavelengths that make up the light. Okay, and you can see that, again, there's very specific wavelengths of light, and in between we don't have any light. So this is kind of strange, and this is difficult to explain if you think that an atom is simply electrons orbiting around a nucleus. And physicists were very interested in understanding exactly why atoms emitted light in this way, because you can just see from looking at this that there doesn't appear to be any rhyme or reason to these lines. Like, they just kind of seem to be all over the place. It isn't really clear why the spectrum is discrete anyways. Like, why wouldn't it be continuous? Physicists didn't really know, and there was no way of answering these questions with Bohr's planetary model. With Rutherford's planetary model, rather. So in this lesson, basically, we're going to talk about a model of the atom that was put forward by Niels Bohr. He published a paper in 1913, which was just 2 years after Rutherford had put forth the planetary model. And we're going to learn that Bohr's model is actually extremely effective at predicting the spectrum for hydrogen. But it's only hydrogen, basically, that it works. It doesn't work for any atom that has more than one electron around the nucleus. So hydrogen, it works great because you only have one electron around the nucleus. But any other element like mercury or neon, it just doesn't work. So it was a good start, though, Bohr's model, and we're gonna be getting into the math of his model in this lesson. If you're curious, I'll just say from the get-go that in order to explain the behavior of atoms that have more than one electron, you need to get into some more advanced quantum mechanics. So we're not going to be getting into that in this course, but we're definitely in a position that we can understand Bohr's model that explains the spectrum of hydrogen. Okay, so it was in 1913 that Bohr put forward this model, and it kind of shocked the physics community when he published the paper because it was based on 3 postulates, and all 3 postulates basically defied the physics that had been established up until that point. Okay, we say that it defied the well-established classical laws of mechanics. Maybe I'll just make a comment and say that this word classical has been used a lot in this unit. What does that mean exactly? Classical physics is simply the physics from before this more modern physics came around. So modern physics started in the early 1900s with Einstein putting forward his theory of special relativity and the development of quantum mechanics. So basically the physics from before relativity and quantum mechanics we call classical physics. So it's kind of the physics from before 1900, basically. And the 3 postulates in Bohr's paper just completely defied classical physics. And these were the 3 postulates. So the first one said that electrons can only occupy certain allowed orbits, and each orbit is characterized by a different specific amount of electron energy. And then the second one, when moving in an allowed orbit, the electron doesn't radiate any energy, so it's in what we call a stationary state. And so this is different from the picture predicted by physicists' understanding of electromagnetism, where you had the electron losing energy through an electromagnetic wave. Bohr said, nope, whenever the electron is in an orbit, it's not going to radiate any energy. It's in a stationary state. And then the third postulate is that the electron can jump from one energy level to another. So it can go from a lower energy level to a higher energy level if it absorbs a photon. And it can go from a higher energy level to a lower one if it emits a photon. And the photon that it emits or absorbs needs to have an energy that's equal to the difference in energies of the levels. And so I thought it might be helpful to just provide a visual of what Bohr's model actually looks like. And in quantum mechanics, you may be catching on that it's kind of difficult to visualize some of these things because our electron, for example, we're saying that it's kind of both a particle and a wave. And in this image, it's being depicted as a particle. So don't take this image too seriously, but to just give you an idea of what the model is saying, it says basically that the electron can only occupy certain orbits. So, for example, it can reside in this first orbit, or it can reside in the second orbit or the third one, but it can't ever be in between. So you're never going to find the electron in between the first and second orbit, for example. And the second postulate said that the electron is stable whenever it's in a particular orbit, so it's not going to lose energy when it's residing in a particular orbit. The third postulate was about how the electron can jump between energy levels. So if this electron absorbs energy from a photon, and that photon has an amount of energy equal to the difference in energy between these levels, that electron is going to jump to the higher level. And then likewise, it can also drop from a higher level to a lower level. When that takes place, it's going to release a photon with that amount of energy. And so according to Bohr's model, basically, he said that these lines come from the electron moving from a higher energy level to a lower energy level and releasing a photon in the process. Okay, so that's his model, basically. Those are the three postulates. And in the remainder of the handout, we're just going to get into the math of it. And so I'll just sketch out how the math worked in Bohr's atomic model. Okay, the idea in Bohr's model basically was that, I'll just scroll up here. Bohr's model was based on the idea, basically, that an orbit is only stable if the length of the orbit is a whole number of de Broglie wavelengths. And so in our first image, we can see that this is an example of such an orbit. This orbit has a circumference that's equal to 3 times the wavelength of the electron. Okay, so 2 pi r is the circumference of this circle. This is the orbital path for the electron, and in this example, it's equal to 3 times the de Broglie wavelength. Okay, and it's kind of based similarly on this idea that you can have standing waves generated for a string. And so the second image is showing standing waves on a string, and you can see that if the string is set up between these two fixed locations, you can have a standing wave generated with a wavelength that's 1/3 of this distance, so that this entire distance from A to B is 3 wavelengths. So it's kind of the same idea that here the entire circumference is equal to 3 wavelengths. Okay, and so he said that the first allowed orbit has an orbital path length of 1 wavelength lambda. And so we can write that like so. And we've learned already that the de Broglie wavelength is given by this equation. Okay, so the de Broglie wavelength is equal to Planck's constant divided by the momentum. And so this is the equation for the first orbit. R1 is the radius of the first orbit. V1 is the speed of the electron in the first orbit. Okay, and then for the second allowed orbit, the circumference of that orbit is equal to twice the de Broglie wavelength. And so twice the de Broglie wavelength would be given by this expression. And then we can kind of generalize this trend. We've written down what it looks like for the first orbit and the second orbit. So we can just write a general equation for the nth allowed orbit. And it looks like this. So basically, if we put n equals 1 into this equation, then we get what we have up here. If we put n equals 2 into this equation, then we get what we have here. Okay, and so to summarize then, according to Bohr, the allowed orbits in the model are determined by this relationship. So we have m vn rn equals nh over 2 pi, where n is an integer. It's equal to 1, 2, 3, whatever integer it may be. This relationship is sometimes called Bohr's quantum condition, because this is really where some quantum mechanics was invoked into the model. The way that we arrived at this relationship was by treating our electron as having wave-like behavior, right? Because here we're dealing with de Broglie wavelengths. We're treating our electron as being like a wave. And so this relationship comes about if we're thinking of our electron as behaving like a wave. And so there is quantum mechanics involved in this. Now, Bohr's model just basically combines that quantum hypothesis with some classical mechanics. So we're just combining the relationship shown up here with some other stuff that we've already learned about in the course, some other classical physics. All right, so in Bohr's model, we have an electron that's orbiting around the nucleus of the atom. And so in that situation, if the electron is orbiting around the nucleus, it's experiencing a centripetal force. And that centripetal force is provided by the Coulomb force. And so in the first part of this derivation, we're just setting the centripetal force equal to the Coulomb force. And so the centripetal force, you may remember, is equal to mv squared over r. And so here we have the mass of our electron, its speed in the nth orbit, divided by the radius of the nth orbit. And then that's equal to the Coulomb force. Now the Coulomb force, the way we wrote it, this is how we wrote it earlier in the course. We said it was K Q1 Q2. Whoops. So K Q1 Q2 over R squared. And so we arrive at this expression just basically by noting that the electron and the proton both have a charge equal to the elementary charge. So E here is the elementary charge. And then R squared, of course, is Rn squared, where Rn is the radius of the nth orbit. Okay, and so we're also going to be using this relationship in order to derive some equations. So equation 1 is simply just simplifying what we have here. All we do, I think, really is just cancel the Rn's. So that's how we arrive at equation 1. Now, Bohr's quantum hypothesis says that m vn rn equals nh over 2 pi. Okay, that's the hypothesis from above here. And so we can solve for Vn in that equation to get equation 2. So all we've done is just solve for Vn in this equation to get equation 2 here. And then we can substitute this expression for Vn into equation 1. So all we've done really is just taken what we have here and put it into Vn. So that gives us this equation. And then we can solve for Rn in this equation, and that gives us equation 3. So equation 3 is an expression for the radius of the nth allowed orbit. So again, according to Bohr's model, you can't just have the electron at any old orbit. It can only reside in specific orbits with specific radii. And so this equation 3 allows you to calculate the radius of the nth allowed orbit. Okay, and so that's equation 3. And then we can substitute equation 3 into equation 2. So we can substitute what we have for Rn here into equation 2 in order to get this equation. Let's scroll down here. And we can actually simplify this quite a bit because there's some constants that are showing up all over the place here. We can simplify it to get equation 4 here, which gives you the speed of the electron in the nth allowed orbit. So that's another useful equation. And maybe what I'll do actually is I'll just put some boxes around our particularly useful equations. So this one's useful. It gives us an expression for the radius of our nth allowed orbit. And then this one is an expression for the velocity. So that's also useful. All right, so we're almost done. You see we're kind of getting to the end here. Now the energy in each orbit is found simply by adding the kinetic and electrical potential energies of the electron. So we're saying that its energy in its nth allowed orbit is found by adding its kinetic energy to its electric potential energy. And so this is its kinetic energy then. Half mv squared gives us kinetic energy. And then this is its electrical potential energy. Okay, you might be a little thrown off by this minus sign, but we did talk about that earlier on in the course. Whenever you have electrical potential energy and gravitational potential energy, if you set the potential energy equal to 0 at infinity, then there is a negative sign. So if that's unclear, you can just refer back to that material, but there should definitely be a negative here. Okay, and so now we can substitute our expression for Vn from equation 4 and Rn from equation 3. So these are just basically our two boxed equations. So this is our expression for Vn. This is our expression for Rn. So if we substitute both of those into this, then we get this, which is kind of messy. But if you go through some algebra, you can find that you can simplify it. And then we get equation 5, which is another one that I'll put a box around, because this gives us the energy for the nth allowed orbit. All right. So this is good. We've gone through some math, and we've found equations for the radius, speed of the electron, an energy for every nth allowed orbit. So this is good. Now, in particular, this equation 5 is a very important one because this is going to give us the energy of the nth allowed orbit. And that's going to help us explain the emission spectra that we saw earlier for hydrogen. This equation really looks like a mess. It is kind of a mess. We have a lot of constants here, but everything is a constant actually except n squared. So n squared is the number for the orbit squared. So I'll just go back to our image of the Bohr model. N equals 1 is the first allowed orbit, n equals 2 is the second allowed orbit, and then n equals 3 is the third, and so forth. So yeah, n squared is the only variable in this equation. The rest are just constants. We have 2 and pi, mass of the electron, Coulomb's constant, elementary charge, Planck's constant. So there's a lot of constants here. We can put values in for all of these constants, and then arrive at this equation, which simply says that the energy of the nth allowed orbit equals minus 13.6 over n squared. And this is if you're calculating the energy in electron volts. Okay, if you typed all of these numbers into your calculator, you would not get minus 13.6. You would get a different number because this first line is showing how you would calculate the energy in units of joules, because we have joules here. Okay, but if you just calculated it in units of joules, it's just a simple conversion to switch it to units of electron volts. And the reason why we switch it to units of electron volts is simply because when we're dealing with the energies of orbits in a hydrogen atom, these are pretty small energies, so it's useful to just have a unit that's very small for energy. Okay, and so this is our equation for the energy of our nth allowed orbit. Now, this equation does a remarkable job, it turns out, of explaining the behavior of a hydrogen atom. And it works equally well for other one-electron atoms. So if you had a helium atom, for example, and you removed an electron from it, so that there's only one electron around the helium nucleus, this equation would also work for that situation. So any atom where you just have one electron residing around the nucleus, this equation works great. But as I said earlier, it doesn't work for any atom that has more than one electron around the nucleus. Basically because this equation doesn't account for interactions between electrons. It's only accounting for the interaction between the electron and the nucleus. So if you start adding more electrons, these electrons interact with each other in complicated ways. And so this equation doesn't work anymore. But it works perfectly if you're just dealing with a hydrogen atom, for example. Now, let's talk about this energy diagram. So this is the energy level diagram for a hydrogen atom. And what exactly is going on in this diagram? Well, you can see the different energy levels for the different orbits. So whenever our electron, for example, is in the first orbit around the nucleus, it has an energy of minus 13.6 electron volts. Okay, that would be if we put 1 into our equation. Minus 13.6 divided by 1 squared is just minus 13.6. So that's where this number comes from. Okay, and then minus 3.40 is the energy of the second orbit. And so that would be found just by putting 2 in for n here. So minus 13.6 divided by 2 squared should give you minus 3.40. Okay, and then to get minus 1.51, you would take 13.6 divided by 3 squared, and so on. So this equation basically gives you a way of determining the energies of the different orbits. Now I'll just return to our original picture of Bohr's model. Bohr said, you'll remember, that when an electron moves from an orbit with a higher energy to one with a lower energy, it releases a photon. And the energy of that photon equals the difference in energies between these two levels. And so that's why you see some arrows that are pointing from higher energy levels to lower energy levels. These are corresponding to basically different amounts of energy that the electron can lose whenever it moves between energy levels. So for example, if our electron was in the second orbit and then it jumped down to the first orbit, it would lose an amount of energy that's equal to the difference in energies here. The difference in energies between the second orbit and the first one. If instead it was in the third orbit and it jumped down to the first, then it would lose an amount of energy equal to the difference between the energy of the third orbit and the first orbit. Okay, so it's important to understand that the electron can jump from like the third to the first without interacting at all with the second one. Like it doesn't have to go from the third to the second to the first. It can go from the third straight to the first. Now, it turns out that you can get different series, as they're called, depending on what energy level the electron is falling down to. So the Balmer series, for example, all have in common that the electron is moving down to the second orbit. And so you get one particular amount of energy released from the electron when it moves from n equals 3 to the second, a different amount of energy when it moves from n equals 4 to the second, and so on. And it turns out that this Balmer series, as it's called, the series that you get from the electron moving to the second orbit, actually gives you the visible lines in the emission spectrum. So let me just scroll up here to our emission spectrum. So for hydrogen, we can see that there are 4 lines that are in the visible part of the spectrum. Okay, so all of these spectrum are just showing us the visible part. And so there's 4 lines in the visible part of the spectrum for hydrogen. And so you can actually find those 4 different amounts of energy in the photons in this Balmer series. For example, when you work through this example, you'll be given the opportunity to find the wavelength of light emitted when the hydrogen atom makes a transition from n equals 4 to n equals 2. And you'll find that that wavelength that results from that transition is a wavelength, I believe it's this one. I think it's the greenish colored one. Let me just check my notes here. Yeah, so whenever you work out the answer to the example in this handout, you'll find that the wavelength of the photon that's emitted whenever the electron moves from the second energy level, or from the fourth rather, to the second, that wavelength is 486 nanometers, which is this line right here. Now you'll see that there are also other series, and these series, by the way, are just named after scientists that discovered them. So I don't know who this Balmer individual was, but presumably they were involved in discovering the spectrum in the visible part of the spectrum. But you can also have energies released in parts of the spectrum that are not visible. So, for example, the Lyman series is in the ultraviolet part of the spectrum. So these are higher energies because the electron is moving over a gap that's larger than we see here for the Balmer series. So you can see, for example, that when the electron moves from the second energy level to the first, that there's really quite a large difference in energies here. And if there's a large difference in energies, that means that the photon released is going to have a lot of energy. And so, as a general rule, photons that are in the ultraviolet part of the spectrum have more energy than photons that are in the visible part of the spectrum, because ultraviolet photons have a higher frequency than visible ones. And then the Paschen series is lower energy than the visible part of the spectrum. So the Paschen series, it turns out, are infrared photons that are emitted for those. Okay, so that's Bohr's model basically. It just says that the emission spectra that you see for a hydrogen atom comes about from the electron just dropping from higher energy levels to lower energy levels. And this equation gives us a way of calculating the exact wavelengths that you would expect from those transitions. Now, the example gives you an opportunity to work this out. So I'll just read the example. I'm not going to go through it for the sake of time, but just to give you an idea of what you're going to work out here shortly. It says, determine with the help of the above figure the wavelength of light emitted when a hydrogen atom makes a transition from the n equals 4 orbit to the n equals 2 orbit. And so, as I said earlier, when you work that out, you'll get an answer of 486 nanometers, which is that line right there in the emission spectrum. Okay, and then you'll see also at the very end of the handout, this is my last comment, I did just provide a summary of basically our boxed equations. So this one gives you the radius of the nth allowed orbit, the speed of the electron in the nth allowed orbit, and then the energy in the nth allowed orbit. And those are also the equations on the equation sheet, just because these are really kind of the useful results from the lesson today. Okay, so again, with these pre-recorded videos, I can't ask if there are any questions, but if you have any questions, do always feel free to just send them to me. But that's pretty much it for the lesson, I would say. So good luck doing the example and the textbook questions, and I hope to see you all on Monday.